Okay. Can you hear me now?
Yes. Yes.
Okay, that was a yes. Okay, so can we move? So I'll just say next slide, and hopefully we'll be. Okay, so to give you a bit, sorry about the technical problems here. Hopefully we'll get a little caught up. So the background so far is that humans have been using graphical symbols for thousands of years, and most of these have not been and still are not tied to language. But about 5,000 years ago, a special form of graphical symbol system was involved that was intimately connected to language, what we call writing. In this talk, I would like to explore how quantitative computational models can help us understand the various aspects of symbol systems, writing systems, and their evolution. Next slide, please. So in particular, I'd like to explore some computational approaches to the following questions. What does it mean to say that a writing system is logographic? Let's say you have an undeciphered symbol system. Was it writing or some other kind of non-linguistic system? And part of the problem, as we'll see, is being clear on what you mean by writing. And another point is that, assuming we're clear on that point, does structure imply that it's writing? And then finally, and this is only going to be a synopsis for lack of time, I'm going to talk a little bit about computational modeling of how writing may have evolved from non-written symbols. And one of the themes that will be kind of going through this entire talk is that computational methods kind of force you to be specific about your assumptions. So next slide, please. So let me start with the first section. This is joint work with Sasha Gutkin, this paper we published in Computational Linguistics last year. Next slide, please. What does the term logography, or if you prefer morphography, refer to? If you look in the literature, well, there are quite a lot of discussion of this, of course, but if you look for actual definitions, a lot of them are quite imprecise, in the sense that if you try to kind of pin down, well, is this logography or isn't it, in the sense of, in the author's, the sense the author intended, it's often very hard to sort of be sure. Actually, one of the best definitions I've seen is recent work by Zev Handel, where he defines a logographic system as those systems where identically pronounced but semantically contrastive elements have distinct graphic representations. And this is the closest actually to the one that we're going to be using here, although I want to point out that Handel has a rather more specific idea in mind. He's specifically referring to the kind of logographic elements that are familiar from Chinese writing. We're using it more broadly. Can I have the next slide, please? So if you look at, there have been various classifications of writing systems over the years, and one that I particularly liked is this old system, this old taxonomy by De Francis, where he divides writing systems basically on the basis of the kind of phonological units that they encode. And within each of these categories, syllabic, consonantal, and so forth, he has a pair of subcategories. One which is kind of pure syllabic, for example, or pure consonantal, and another one which he calls morphosyllabic or morphoconsonantal. So the fact that there's this kind of morpho-X branch in each of the main phonological categories suggests, next slide, please, that these are really orthogonal dimensions. And so next slide, please. In my book in 2000, I proposed actually splitting these out into two separate dimensions. One where you have the type of phonography, and this is, well, there's been recent discussion at this point by Osterkamp and Schreiber, but basically it's kind of categorical. Something's an abjad, or it's an alphabetic system, or it's an abugida, and so forth. And then there's the amount of morphography, or amount of logography. And that's really a graded notion. It's not, something is either logographic or it isn't. Now, I proposed this in my 2000 book. Rogers, in his 2005 textbook, took this up. So I'm actually using Rogers' version here. Next slide, please. So just to, pin down one point, right? You might, those of you who sort of think in terms of, well, logographies, that's stuff like Chinese or Japanese. We didn't invent the idea that you could call basically alphabetic systems like English, logographic. So for example, Sampson in his book, and many other people have made this same claim, have argued that English has a great deal of logography, basically because you spell different words according to basically different words can be spelled differently even if they're pronounced the same. Or for example, in the case of Persian use of Aramaic writing system, there are these so-called heterograms where you basically use Aramaic spellings of words, like the word for king would be spelled as it would be in Aramaic, but it was intended to be pronounced as it would be in Persian. And again, this was an instance of logography in a very otherwise clearly segmental system. Next slide, please. So if it's a matter of degree, you ought to be able to measure it. Now, I didn't propose such a measure, neither did Rogers. Penn and Schomer, in a paper in 2006, proposed using correlation coefficients, but I don't have time to get into this here, but in our paper, we argue that this, in fact, doesn't work. One measure that does seem to work well is the amount of attention paid to the context by a neural sequence-to-sequence model that is trained to spell words in context. Okay, so let me, next slide, please. Let me explain what I mean here. So let's say you're training a system to spell a given word. So you're giving it a phonetic transcription, like, let's say the first word of the English book of Genesis, the first sentence of the English book of Genesis. You're giving it a phonetic transcription. In this case, the phonetic transcription happens to be an alphabet, but that doesn't matter. And your task is to spell, say, the third word. Okay. So next slide, please. So the kind of model we're using is an attention-based recurrent neural network model. This is a very familiar kind of simple neural language model. The particular example here I'm showing is for English translation from English into French. There's a lot of components to this model, but the part I want you to pay attention to is this, this part called the attention portion, where basically each of the output positions has an attention vector associated with it. And that attention vector kind of, once the model is trained, gives you gives you some clues as to what the model is attending to in the input and the output when it tries to predict, for example, that I in English should be translated as je in French. Now you can combine these vectors into a matrix, and that will give you a visualization of how the model is paying attention to its context for basically for the whole sentence. So in our case, the input is phonemes and the output is, well, what I'll call graphemes, for the lack of a better term for the present purposes. Next slide, please. Next slide. Yeah, okay. So let's say you have a highly phonemic writing system. Finnish is a good example. The idea is that, so here's an attention matrix. On the horizontal axis, we have the phonemes. On the output, you have the prediction of the spelling for the given word. In Finnish, since it's almost like a one-for-one mapping between written form and phonemes, not surprisingly, you don't have to look much outside. In fact, you don't have to look at all outside the word in general to see how to actually spell a given phoneme. Next slide, please. But in Chinese, for example, so if you take the Chinese morpheme shi, meaning B, and in this case, for reasons which we discussed in the paper, I'm not going to get into it here, but for reasons we discussed in the paper, we actually don't predict the actual character, but rather the changjie, which is an input system for Chinese, the changjie encoding of that character. So this is mapping from the phoneme sequence as represented in pinyin into the changjie representation. But the basic point to pay attention to here, to notice here, is that the attention is all over the map, and that's not surprising, right? Because in Chinese, in order to know how to write shi, you have to basically look more broadly than you do know how to, you have to look when you try to spell something in Finnish. Next slide, please. Okay, so how do we actually use that? So, basically it's pretty simple, right? You have this attention matrix. Imagine the one at the top is the kind of random, this random thing is a kind of an attention matrix. And you want to look how much of the activity is outside the rectangle that corresponds to the word you're trying to spell. Okay, so you can represent that rectangle as in the second block here by this blue thing on yellow, and you can basically use that to mask out the region and that corresponds to the word, and ask what percentage of the total activity is outside of that block. Okay, so that's the basic idea. Very simple measure. Turns out, there are two ways you can interpret that. A word like the word "shi," for example, in Chinese occurs a lot. So one way to measure it would be simply to look at all of the tokens in your corpus and basically say, okay, you're going to sort of get an average measure for the entire corpus over all of the instances of that word. But of course, that's going to weight the word "shi" a lot because it's just a very frequent word or a very frequent morpheme. So another interpretation, another formulation would be as a type measure. Okay, so we had both a token and a type measure, and we'll see both of these later on. Next slide, please. Okay, so we also considered other measures, lexical measure, which is simply, basically counting the spelling variants for a given phonological form in a dictionary. That also has both a type and token interpretation. Also an entropic measure where we compared the bigram conditional entropy of the written form versus the phonology. Bigram conditional entropy is basically a measure, well, this goes back to work by Claude Shannon from the 1940s. It's basically a measure of how much information or how much predictability there is in the system. The higher the entropy, the less predictable a system is, or the less information there is in the context. The lower the entropy, the more predictable, the more information. And you can kind of see how that's relevant here in an ideal phonographic system, right, where everything was a simple one-to-one mapping between whatever the phonological form is and the graphemic form. There isn't any more information in the written form than there is in the spoken form, but in the case of a highly logographic system, there's presumably a lot more information in the written form than there is in the spoken form, or at least there's a different amount of information. And you could, by comparing the two, you might come up with a measure of logography. Okay, next slide, please. Okay, we used a bunch of corpus. Our basic corpus was the Bible corpus, which is this multilingual collection of Bible translations. We used automatic open source phonetic transcription systems to get the pronunciations of words. Obviously, that's far from ideal, but we don't have the resources to go through and actually get the real pronunciation of every word in context. It turns out in the paper we compared this with using some very high quality automated proprietary systems, and it didn't make a lot of difference to the results. In the interest of time, next slide, please. So if we get back to Roger's taxonomy again, and we sort of pick out the languages that he considers that we also consider. We had Finnish, Korean, Russian, English, Chinese, and Japanese. And the relative rankings that Rogers gives, I mean, sort of background here, right? There's no gold standard of the amount of logography. We're kind of developing this idea in this paper. But it's reasonable to compare it to an independent writing systems expert's intuition. And, according to Rogers, Finnish is very non-logographic, Japanese is very logographic, Chinese is somewhat less logographic. And, you can sort of say, well, a lot of people might agree that with the ranking that he gives. Next slide, please. So how do the different measures fare? Well, the lexical measure is kind of okay, except it has a kind of a weird, ranking for Korean for some reason. Next slide, please. The entropic measure is also okay, but depending on whether you're using the token or the type interpretation, it either ranks Russian in a weird way, saying it's more, phonographic or less logographic than Finnish, and similarly for Korean. Next slide, please. Finally, the attention-based measures, in particular the type-based interpretation, seems to, for what it's worth, right? Again, there's no real gold standard here, but for what it's worth, seems to agree with Roger's intuition. Next slide, please. Okay, so to summarize this section, we've compared various measures based on simple lexical counts with entropy and base measure. The attention-based measures seem to accord better with intuition for what that's worth. We tried more sophisticated neural models, transformers, temporal convolutional models. They had about the same performance, but they were actually much harder to interpret. We also argued in the paper that the results correlate to the extent that there are such studies with comparative studies of the acquisition of spelling. Okay. So the conclusion is you can measure the degree of logography in a way that seems to accord with intuition. The model seems to make some intuitive sense. If you think about it, right, if a system's very logographic, you need to look more at the context, right? Logography isn't binary. That's maybe not proven by what we've done here, but at least is, you know, consistent with what we've done. Sorry, let me stop that. You know, logography isn't binary. Would argue it's basically graded. And the other point, which I didn't have time to get into here, is that the amount of logography in a system also depends on what you define the target to be. If I'm trying to spell a morpheme, well, you know, you might require more looking outside of context than if you want to spell a word or some larger unit, right? So the larger the unit, the less you probably need to look outside the context in order to determine how to spell it. Next slide, please. So in the next section, I want to talk about how you might use statistical methods or not use them to determine whether a system was a writing system or not. Next slide, please. So we'll see there are two recurring problems, fuzzy or intentionally, possibly, or in any case, unclear definitions of the notion of writing, and a fallacy, which unfortunately is very common, namely that structure, which we can also call syntax, implies syntactic structure. Again, computational methods force you to be precise on these points. Next slide, please. So how do you tell if an uninterpretable system is writing? You've got some ancient system, right? You don't know what it is. Can you look at it and say that it's writing? Can statistical methods tell you this? Well, first of all, you know, if there are only single symbols or symbols repeat too much, right? Or symbols repeat in funny ways, you probably guessed it isn't. So next slide, please. You know, nobody probably would think this is writing. These are Pennsylvania barn stars, or they're also called hex signs. You find these on barns scattered around the various German heritage areas of Pennsylvania and other parts of the eastern United States. If you look at the quote unquote texts, you can see that they are symmetric in funny ways. They don't look like writing, right? Next slide. But, you know, what if there are texts and the text system seems to have some kind of structure? Next slide, please. So, you know, here's 4 examples. Now, many of you probably already know all of these, but in any case, I'll just leave you with that question. I mean, what are, you know, which of these is writing and which of them is not? Are they all writing? Next slide, please. But, you know, first of all, let's pin down what do you mean by writing, right? If you go back to De Francis again, he makes it very clear there are 2 kinds of, you know, views on writing systems. Those are you call inclusivists. So writing is basically any system of graphical symbols that is somewhat conventional and is used to convey information. And then there are the exclusivists. Writing is only those systems of graphic symbols that encode linguistic entities, morphemes, syllables, things like that, and thus basically parasitize off of language and thus allow you to convey any information that can be conveyed in natural language. Now, there are inclusivist definitions out there. Powell, for example, in his 2009 book, defines writing as a system of markings with a conventional reference that communicates information. There's no reference to language there, right? Next slide, please. So, you know, can you use statistical methods to tell you whether a system is writing or not? Well, let's first of all be clear whether you're an exclusivist or an inclusivist. You can be either one, but be consistent. If you want to be an inclusivist, then all you need to show, if you follow Powell's definition, is that the system was conventional and the system conveyed information of some kind. That's a pretty low bar, right? I mean, you can often tell if a system is conventional. For example, if symbols occur in lots of text, the same symbol occurs again and again. It probably was conventional. Probably was conveyed information, because otherwise, you know, why would people have used these symbols if they weren't trying to convey some kind of information? That's a low bar, and it's not usually something that actually requires statistical techniques. You should also be aware that if you say something was writing, the person on the street is probably going to interpret it to mean that it's something like what you're looking at on this slide, that you could use it to write novels or shopping lists or whatever, right? That's the sort of the layperson's interpretation of what writing means. So typically those who would want to make a substantive claim start by, as exclusivists, right? Second point, structure does not imply that the system encoded language, okay? Next slide, please. So getting back to our examples, sure, as I said, everybody knew this. So you've got Mayan writing, Egyptian writing, Luwian writing, and then the thing on the left is not writing. This was basically a non-linguistic symbol system that was used in Babylonia. They're often called kuduru stones, or kudurus. The symbols on there were symbols of deities, which were favored deities of the person with who had the property, and they would often array these on stones in texts. And in this case, you can kind of guess that it's not writing because below the deity symbols, there's actual cuneiform writing. Next slide, please. So I want to talk about something which some of you may be familiar with, the Indus Pictish controversy, which spanned out over about a decade. There were these, texts from the Indus Valley civilization, which are Bronze Age civilization, one of the largest Bronze Age civilizations from the 3rd millennium BCE. It's characterized by these cryptically short texts in an otherwise so far uninterpretable system, and then Pictish symbols from Iron Age Scotland. Next slide, please. Okay, so just to sort of give a brief synopsis of the timeline here. So in 2004, my colleagues and I published a paper where we argued that the Indus Valley texts were not actually writing, at least not in the exclusivist sense, okay? In 2009, Rao and colleagues published a paper in Science that purported to show entropic evidence for linguistic structure. And there were various other papers that followed. Inspired by this, in 2010, Lee and colleagues published a paper that claimed that Pictish symbols were revealed as written language via what they call Shannon entropy. And both of these were critiqued by Liberman in the language log. I published a critique in Computational Linguistics in 2010. There were replies by Rao and Lee. In 2014, I published a paper in Language that included a much larger set of non-linguistic systems and writing systems and a much larger set of different methods. And I'll get to some details of that later on. I'm just going to focus on Lee et al.'s proposal here in the interest of time. The reason I'm doing this, though, is that, these papers still get cited by people today who believe the results. Next slide, please. So, for example, there was a paper that appeared a few months ago on restoring, using neural methods to restore missing bits of ancient text. It included some people from DeepMind in London, and they cited Rao et al.'s papers, actually several of them, including, oddly, the reply to me, that involved what they call traditional machine learning approaches. Well, the people at DeepMind should know better. There was nothing machine learning about the original approaches that Rao et al. Used. But in any case, next slide, please. There was also a paper that actually got quite a lot of attention in the popular science press recently, which purported to show that the neural spiking the electrical spiking activity of the myceliae of 4 different species of fungi showed language-like patterns. And the author here again cited Lee et al.'s paper as having demonstrated that the Pictish symbols were writing. Next slide, please. Okay, so I'm not going to argue here that whether the Pictish or Indus symbols were writing or were not. The point is simply to show that the statistical methods are not as informative as people think, and that a lot of the discussion has really been based on fundamental misunderstandings about the issues. Next slide, please. Okay, so in a nutshell, this is Lee et al.'s proposal. They claim that their method is robust to small sample size. Well, that's good because the Pictish corpus is very small, okay? They basically used bigram conditional entropy, or they based it on bigram conditional entropy. Now, we saw this briefly before. Again, it's a measure of how much information or how much uncertainty, if you like, there is in the system. Now, Rao et al., just as a side note, actually used this more or less out of the box in their original paper. But Li et al. Have a somewhat more sophisticated use of it. They actually have developed two measures. One they call U, where they use bigram conditional entropy, which for some reason they notated as F, divided by the log of the number of unigram types, sorry, the number of bigram types divided by the number of unigram types. And then there's a measure C, which uses the straight rather than logarithmic form of the denominator of the previous expression, so nd over nu, plus a constant, which they determined by cross-validation to be 7, that's A, plus the total number of bigrams that occur once divided by the total number of bigrams. For those of you familiar with corpus linguistics, statistical measures of corpus linguistics, you will probably recognize this term as the good Turing estimate of the probability mass of unseen events. It's basically a measure of how likely it is that the next thing you see from a distribution is something you've never seen before. It's a measure of productivity. So they use these two measures to train the decision tree. They trained it on various corpora, writing systems, Morse code, heraldry, and so forth. Next slide, please. And this is what the decision tree looks like. The first branch splits on values of C. Everything to the left is non-linguistic. Everything to the right is linguistic. And then it splits on various values of U. They actually purport to classify things as letters, what we would call alphabetic systems, syllabic systems, and then words. And for them, the Pictish symbols fall into the words category. So they conclude that the Pictish symbols are lexicographic in nature, in other words, what we would call logographic. Next slide, please. Okay, so as I mentioned, I published a paper in 2014 in language where I looked at a much larger set of non-linguistic systems. So I looked at, among the system I looked at Asian emoticons, which are these, I'm sure you've seen these things where you take arbitrary symbols from the Unicode code, basic multilingual plane, and you concatenate them together into things that look like faces. So it's obviously a non-linguistic use, but you can kind of treat these things as non-linguistic texts. Pennsylvania barn stars we've seen, the kudru, so the Babylonians, boundary stones you've seen, Pictish symbols you've seen. Totem poles, these should be familiar to many people, right? These were used by the many ethnic groups in the Pacific Northwest, basically large tree trunks with symbols carved on them, okay? Vincha symbols, very early Neolithic symbol system from the Danube Valley region. Nobody knows what they meant, but they left behind these cryptically short texts, and then weather icon sequences. And then a bunch of different linguistic data. Now, fortunately, Li et al.'s approach classified all of the linguistic corpora as linguistic, not necessarily the right kind of linguistic writing system, but they were all classified as linguistic. But next slide, please. It didn't fare so well on the others. It basically classified everything as linguistic, except for the Vincha symbols. Next slide, please. So yeah, it got one right. Okay, next slide, please. Okay, so as I mentioned, I tried a bunch of other things. Something that worked actually surprisingly well was a rather stupid measure based on two measures of repetition: capital R, which is simply the number of tokens in a text that are repeats, and little r, which is the number of tokens in a text that are repeats and are also adjacent to the token that they repeat. So let's take the text A, B, A, C, D, B. Capital R would be 3 because you have 2 A repetitions and 1 B repetition, and little r is 1 because you have one instance of A repeating and is next to another instance of A. So the interpretation is that if you have a high value for this ratio, it means that the system has a lot of local repetition compared to the total amount of repetition. Okay, so if you look on the right, actually this gives you a fairly nice split for most systems. It massively misclassifies some cases like Sumerian. Okay, it also is a little bit on the boundary with Egyptian and Mesopotamian deity symbols, but everything else kind of falls into place. Next slide, please. So I also trained a decision tree classifier. And basically, to cut a long story short, on most divisions of the data, it actually, where you took out the Indus systems and the Pictish symbols from the training data, if you then try to use the model to predict, is the Indus system, for example, linguistic or not, most of the divisions of the data classified the Indus system and the Pictish symbols as non-linguistic. Okay. Now, again, the repetition measure R over R is kind of simple, but interestingly, both it and Lee et al.'s C sub R measure, remember, there was one of two measures that was important in their classifier, both correlate with text length. Okay, turns out the non-linguistic systems tend to have shorter text. That's kind of trivial and stupid, but it's actually more important than you might think, because if you think about it, if you have a system which can only be used to basically write short text, you might look askance at whether that's really a full writing system. Okay, I don't want to claim these results are definitive by any means. I've never claimed that. But if you want to take seriously the implicit claim of the other authors that statistical methods are useful, then if someone comes along with something else and says, okay, we've tried this on a bunch of systems and it classifies things in this way, and I'm sorry, this classifies your results differently, you kind of have to take that seriously. Needless to say, that often doesn't work out that way. Next slide, please. So, just a quick overview of Lee et al.'s response. So they, in their original paper, they clearly presented an exclusivist approach. It was very clear from their discussion. In my 2010 reply, I used their method to show that the Kuduru Babylonian symbols were words. Now, to their credit, they actually replicated my result, and they were fine with that. And they said this was a difference in viewpoint over terminology as to the definition of what constitutes writing. And they quoted Powell, the definition we saw before. So now they've switched to an inclusivist approach. Okay, so now using an updated version of the Babylonian corpus in 2014, I actually ended up classifying the Kuduru symbols as syllables. So the method is quite unstable. You add a few texts here, a few texts there. It can push things over the boundary, so that's not terribly surprising. But it was still classifying it as linguistic. But now all of a sudden, in the joint reply from both teams, which is Rao et al. 2014, they're now claiming that I misrepresented them and that their method was developed to try to develop the level of communication that a character communicates at rather than the definition of writing. Now, I actually don't know what this means, but putting that to one side, I mean, their original paper did claim that the method revealed Pictish symbols as written language, right? So I'm not sure, what's going on here, right? They seem to have changed position. I suspect, unfortunately, the one thing that happened is in the 2014 paper, I had a lot more obviously silly results if you apply their method out of the box. And therefore, it's a little harder to square those results with, what they were trying to show. Next slide, please. So, okay, massive inconsistency in the definition of what people mean by writing. What about structure? So Rao and colleagues frequently refer to the so-called rich syntactic structure evidence in the Indus texts. So if entropic measures are useful at all, they ought to be able to distinguish structured symbol systems from ones that have no structure. Fine. Actually, it's not clear that they do. So Lieberman, for example, in the language lot, showed that if you take an obviously non-linguistic system, you basically just randomly toss 7 cubic dice and record what you see in terms of the numbers. These texts that are generated are classified as a syllabic writing system by, say, Lee et al.'s method. Anyway, but suppose they did reveal structure, what would that tell us? Next slide, please. Well, actually, it wouldn't tell us very much, right? Lots of non-linguistic systems have structure. Here's an example from music and mathematics. Just in the interest of time, we'll just look at the mathematics case, right? So this is a partial differential equation, the wave equation. There are rules on how you combine symbols, right? So I can put the partial differential symbol before the variable it goes with, but not afterwards in conventional usage. There are various other conventions on how you combine symbols. Okay, there's clearly structure here. Next slide, please. But my favorite example is when you compare British heraldry with Japanese heraldry, which is called Kamon. there are a lot of similarities between the two systems. They were used to represent clans, individuals. They were often used in battle to identify armies. And so as a result, they both had to be easily identifiable from afar so you could, tell who your friends and your enemies were. Both of them, various other properties. Another property that they both had in common was that it was common for the motif to allude to some property for of the family name. So in the case of heraldry, there are these things which in English are called canting arms, in French, arme parlante. And here's an example here from Wikipedia where the Bose-Lion family has, well, bows and lions on it, okay? And in the case of the Kamon, you get allusions in terms of, for example, here, this one uses the falling wisteria motif. Wisteria in Japanese is Fuji. This is for the Fuji family, which literally means wisteria well, okay? So they're using a motif which relates to their family name. Next slide, please. But there's also an important difference. The Bose-Lion case, Bose-Lion, I should say, case illustrates one property of heraldry that is not found in Kamon, namely quartering. And quartering occurred when a wife who was an heiress with children dies. And when she died, the son could take the arms of his mother and the arms of his father and quarter them. And so presumably that's what's going on in the case of the Bose-Lion case here. You've got the arms of the mother, which would have been Bose, and the arms of the father, which would have been Lion. And those are quartered. But there are other ways you could represent marriage. Another way would be by what was called impalement. So if the wife was not a heraldic heiress, the husband could impale her arms on the left, that is sinister side of his arms. So this is illustrated in the example below, where the circle thingy is the wife's arms and it's on the left-hand side. That's left from the point of view of the person bearing the arms, so therefore from the viewer's point, the right-hand side. That was another way language could be represented. That was another way marriage could be represented. But if she was a heraldic heiress, then another way you could do it would be to place the arms over his arms in what was called an escutcheon of pretense. And you see an example of that here, okay, in the right-hand side here. Next slide, please. Okay, so quartering was theoretically unbounded. And I've never been quite sure whether the example on the left is real or not, although you can certainly find this example, but perhaps a more realistic example is the one on the right, where you have two levels of quartering and an escutcheon of pretense on the top too. Okay, so there's quite a bit of structure in the system. Next slide, please. But there's no equivalent of any of these devices in Kamon, and there's a simple reason for that. In Japan, from basically the late Kamakura period onwards, in marriage, only the male line was considered important. So much so that there was even a tradition which was called mukoyoshi, where a family who did not have a male heir could actually adopt a male adult as their son. And many families have done this, in fact, including, companies have kind of kept the company within the family by adopting an unrelated male as the son, and he would take the name and so on and so forth. So this was because effectively women had no status in traditional Japanese society. It wasn't that they couldn't have emblems. There were a whole sequence of female mon called onnamon, and these were only, however, inherited in the female line. Typically, they went from mother to daughter. There were other ways of adoption, but they were never incorporated into the husband's mon. And so you have two systems that were similar in many, many ways, and the only point of divergence was was in syntactic complexity, and that boiled down to a simple difference in cultural constraints on the use. Next slide, please. So, of course, why am I bringing up heraldry, right? Heraldry, nobody would think the heraldry is written language. Syntax is two-dimensional, and writing systems, two-dimensional arrangements of symbols, always very, very local, right? Writing macroscopically is linear, basically. So nobody was going to think heraldry is writing. So why am I even raising this issue? Next slide, please. Well, I will just point out that if you look at what the Pictish symbols actually look like, They're quite two-dimensional. I'm not going to claim their syntax. We don't really know, right? But the only way in which they look linear and therefore like writing in any sense is in their electronic encodings. They don't look like writing at all when you look at the Pictish stones. Next slide, please. So structure is not equal to linguistic structure, right? Structure in a system derives from what the system is used to represent. It implies nothing about whether the system represents language or not. So the real question is, not whether your method can detect structure, but whether your method can specifically detect linguistic structure. So far, I've not seen such a method. Next slide, please. So just in summary, statistical methods are kind of a double-edged sword, right? You can't just pick the methods that show what you want. You need to be consistent in what you use. When you use terms, right, there's been an immense amount of confusion, and still is immense amount of confusions by fuzzy ideas about what constitutes writing. And structure in a symbol system relates basically to whether the information you're trying to encode itself has structure. So that should have been obvious from the get-go, but for some reason, it's a point that's often missed, okay? So, I think the results of computational approaches have so far been mostly negative, but they've kind of laid bare important inconsistencies and fallacies. Okay, so next slide, please. I'm going to go through this very quickly, unfortunately, because a little short of time at this point. Next slide, please. So I've done some work on, the modeling the evolution of writing from, non-linguistic symbol systems, and the basic idea of the simulations. These are computational simulations, right? Is you generate artificial languages that have various phonological properties. They could be mostly, basically monosyllabic, maximally disyllabic morphemes, or maximally sesquisyllabic morphemes. Okay, a morpheme is just an association between a phonological form and a concept. We basically initially randomly associate a small number of concepts with symbols. Okay. We then generate a set of texts in each language that pair the symbol, either just the meaning with symbol strings or the meaning plus the phonetics with symbol strings. And we train a neural model to produce symbols under these two conditions. And what I'm reporting here is in forthcoming work. And then we want to observe how the model extends to new meanings or new meanings plus phonetics messages. Okay, so does the model kind of extend to new things, and to what extent does it do so? So we then iterate the process and see how it evolves over time. Next slide, please. So, imagine, let's take a sort of Mesopotamian accounting, kind of a silly slide, but Mesopotamian kind of accounting context where you've got an accountant who wants to write down 4 cows, 3 horses. We assume that they know what the symbols mean. So basically, if you're just sort of mapping the concepts, which is represented in the left-hand side of the table on the left, with the written symbols, where we take, emoji to represent the commodities and Roman numerals, because why not, to represent the numbers. And basically, we're going to train a system to map from the stuff on the left to the stuff on the right. Okay, but now imagine, next slide, please. A context in which somebody's actually kind of dictating the accounts. The hypothesis is that writing evolved in a context where people were effectively being told, okay, write down 4 cows or whatever. And that would sort of train the brains of the accountants or whoever the people who are writing these symbols down to associate the symbols with particular sounds. Next slide, please. So you've got this overseer who's saying, these are nonsense artificial languages. So semsoc means 4 cows, right? Okay, so now you can train it with both the input, the meaning, because assume the accountant knows what the meaning of the symbols is, but you also have the sounds in here. Okay, next slide, please. So what comes out of the model, and again, lots of details I'm skipping over in the interest of time here, but basically is that one observation is that monosyllabic languages and also sesquisyllabic languages are far easier to generalize. That is, more new terms become writable as you iterate the process of training, regenerating text, retraining the text, and so on and so forth over multiple generations. And this accords with ideas that have been around actually since the mid-19th century that suggest the importance of syllables. Okay, next slide, please. Contrary-wise, disyllabic languages tend to be much harder to extend. Next slide, please. But when you do extend them, it tends to be more in terms of semantic extensions, but in turn, these are much less productive, if you like, than phonological extensions. Okay. So next slide, please. So, the simulation mimics some of the things we know about the early evolution of writing. Symbols could be extended both on the basis of the meaning and the sound, but the phonology is more productive as a means of extension than semantics is. And, that seems to be true, right? People who have tried to develop purely semasiographic writing systems have never succeeded. Phonological properties of the language are important. We know this, right? It's easier to develop a system in a monosyllabic language, language where most of the morphemes are monosyllabic, than ones which have longer morphemes. Okay, and this, I think, is basically fairly trivial reasons, right? I mean, it's just easier to find a neighbor in that's phonetically close to another monosyllable than if you go to disyllables. It's just much less likely to find a neighbor that's close by. Next slide, please. Next slide, please. So to summarize, I promised in the abstract that I would sort of map out a few new directions. So, I think we need some more work on understanding the difference among different writing systems. That relates to the first part of the talk. Our stuff on logography was, just one of the kinds of things you might do. I think that, the jury is by far from out on the issue of, whether you can determine a system's function just by looking at the system symbol distributions. I don't think you can, but somebody could prove me wrong. And a crucial point that I tried to emphasize before: can one really distinguish structure from specifically linguistic structure? That's the crucial point if you want a statistical method that is going to tell you whether something is writing or not. Okay, and finally, I'd like to do, suggest that you could also do more sophisticated simulations of the evolution of writing. For example, we could go from real images of glyphs and real speech. It's not hard these days to put together tools that will do this kind of thing. There's lots of open source, deep learning systems that allow you to actually do a much more realistic simulation, if you have the compute power to do it. Okay, and finally, many of you may have been expecting me to say something about, there's been a lot of recent work on automated approaches to decipherment, recent work, for example, by Regina Barzelay's group at MIT. There's a couple of recent papers by Lohr et al., which, by the way, all of the reference here are online, and I have a link to an online page, which is in the slides. So once the slides are shared, you'll be able to get all the references. I have a critique of the latter paper, the Lohr et al. 2020 paper in a blog. But basically, just to sort of summarize, I'm kind of skeptical of this work for several reasons. First of all, when everything they've shown is obviously, kind of post hoc decipherments of systems we already know, and that's fine. Of course, you need to show that the systems actually do something. But over and above that, for the systems that we haven't yet deciphered, right, I think there are unrealistic expectations in a lot of this work about, finding related languages. So the Ugaritic decipherments that they've proposed, for example, depend on the fact that Ugaritic and Hebrew are very closely related. You might not have a language which is related at all to the language that underlay whatever ancient writing systems you're trying to decipher. And the other issue, of course, is the complexity of the writing system. So, it's much easier in principle to use these methods to decipher a segmental script for a language with a closely related known language than it is to decipher a mixed syllabic, semantic syllabic script for an unknown language. Okay. And again, there still remains the problem of small sample sizes. So we have 5 minutes left on the official schedule. I actually only used 48 minutes of the talk time. I'm not sure how you want to do this, Giannis. It's up to you. But anyway, I will now open this up for questions.
Thank you. Thank you. So we will stop sharing. Any questions? Any questions online? Daniel? So, if you want to ask a question, send me a message on my chat. So I didn't got any message. No questions. Yes.
You said, Antonio Perri, you said that in your opinion, writing is macroscopically linear. What do you mean exactly by?
Well, I mean, if you look at the you know, the slide, for example, I don't know if you know, if you, I mean, basically it means that, you know, there's no interesting use of the second dimension. I'm not talking about artistic uses of writing where you can sort of have the written form going around in circles and things like that. I'm talking about in the normal everyday use of writing. You know, basically it's right to left or left to right or top to bottom in a line, right? So if you look at Chinese writing, right, within the Chinese character, there is, you know, there is interesting two-dimensional relationships of components. So the semantic component and the phonological component of a Chinese character can be arranged left to right, right to left, top to bottom, whatever. There's various ways you can combine these things, but the overall arrangement of text in Chinese is linear, right? It traditionally goes top to bottom.
But we are faced of the fact that in many writing tradition, also in glottographic, alphabetic one, there are texts which are based on non-linear arrangement of units in a text. These are basically no usual or unmarked use of writing, but they are. When you find a tabulation or when you find some cross-reference in a spatial plane of representation, you will find always arrangement and assemblage of signs by their disposition, which is in many cases meaningful for the understanding of the text.
Well, just to be clear, right? I mean, there are tabular arrangements, for example, where, for example, in ancient accounting text, you see, you know, here's a commodity, here's the number of that commodity, here's another commodity, here's a number, and it's sort of the tabular arrangement is important. I'm not saying you don't have two-dimensional uses of writing, but if you're just saying, how do I write down a simple sentence in the language?
You think about the.
I'm sorry?
You think about the structure of the system, not in the use of the specific kind of text.
Right. I mean, you can definitely use it in a two-dimensional way, but inherently there is no two-dimensional aspect to macroscopically in writing systems. I think that's true.
The language just has to be highlighted that there is no bidimensional features. Okay, understand.
Thank you. Any more questions? Yes. So one last question, and then we move to the next speaker.
Thank you. It's Mark Huster, and I have an almost naive question. If for the Indus system, whatever it happens to be, there are too many unknown parameters, like the underlying language, is it writing, isn't it writing, or whatever it happens to be, do you have, based on your models, an idea, and it stands to reason that if the corpus is very small, like it is in this case, it's impossible to make a meaningful decision on it or take a clear opinion on it. do you have an idea of what would be the minimum corpus size where you think statistical methods could start to produce meaningful results? Or
well, I mean,
corpus size?
yeah. So I mean, there is a notion of you know, Shannon had a minimal notion of what you could use to decipher a system. I'm not sure that directly applies here, but I mean, you know, I can't give you an exact number, right? It's clearly, but it's not just the corpus size. It's also the fact that the individual texts of the corpus are also very short, so they don't give you a lot of. None of the texts have a lot of information in them, right? They're very, each of the texts. So you know, if you found, for example, a very long text, that may not be enough to decipher it, but at least you would maybe give you a little bit more sense that this probably must have been some kind of writing system, because then you would see that there was, presumably the symbols would have repetition patterns which were more similar to what you would expect to see in a writing system and so forth. But you know, it's not just the total corpus size, it's also the, you know, the fact that you have these long texts. Very short text, right? So, I mean, if this were a simple, if this was a writing system and it was a simple phonographic writing system, say a simple segmental writing system, which is highly unlikely, then you could, you know, use, you know, some of the measures that have been proposed as kind of the minimum amount of stuff you need to decode. But of course, again, this would also presume that you know what the underlying language is likely to be. So it's hard to give an exact number, but the answer has got to be that it's got to be a lot more things would have to fall into place before the system becomes really decipherable, in my view.
Okay, thank you very much, Richard. So maybe we can give him an applause.